Hi, everyone. Let me just start off by saying I'm extremely exhausted, so I apologize in advance if I maybe sit down at some point in the middle. I'm going to tell you guys about some work that I've done. So it's work together with Eric Kuflick and with Hitoshi. And it's called Dark Spectroscopy. And it's based on two papers we put out. The first idea was sort of embedded in this paper from over a year ago, and then we had a recent paper just around 2 weeks ago. So it's a really simple idea, so I think hopefully the talk will be very short. I just want to sort of give you guys, this is actually also the brief outline. I just want to show you guys what the idea is and then sort of demonstrate it on a few dark sectors. Okay? So what do I mean by dark sectors? Well, as we all know, these dark sectors are abundant in, at least conceptually, in particle physics, although we haven't yet discovered any of them. So this could be something that arises, maybe in the context of dark matter, some strongly coupled theories or some weakly coupled theories, maybe regardless of dark matter. And what I mean by dark sectors is just that there could be some, instead of just one new particle for new physics, maybe there's some complex sector that can exhibit some very rich dynamics. And with these rich dynamics, you could also expect to perhaps have a wealth of resonances in the sector. So what I mean here by dark spectroscopy is we're going to be talking about some method in which we could probe or see these dark resonances. Okay? And the idea is extremely simple. So just think about QCD. Okay? So how do we know the resonance structure of QCD? What do? We take E plus E minus, we smash them together, and it produces all sorts of stuff. Right? So we have some collision at center of mass energy square root of S. E plus E minus goes to something that's going to some hadronic stuff. So let me just call this let me just write this down as some particle, something V. This could be the photon, this could be the Z, this could be the wealth of resonances, and it's decaying hadronically. And what happens here is that as we scan this square root of S, so if we do these collisions at a variety of different center of mass energies, we're scanning this stuff. Okay. And when we do this, this is how we get a beautiful picture that I'm sure everybody's fully aware of. So this is usually written down as the cross-section of E plus E minus 2 hadrons, normalized over the cross-section to muons. And there's this beautiful picture in which we see the rho and the omega. We see a phi, j psi, psi 2s, etc. And at some point, we also see the z. Okay, so this is as a function of square root s. In GV, we see all of these particles. Okay. You can ask yourself, how could I be able to see this if I wasn't looking at scanning square root s, but rather I wanted to look at a fixed energy machine? So how could I do this? Well, I could take exactly the same process, now just add on a photon. So by looking at this photon is essentially a tracer for the system it's recoiling against. So if all I was doing was looking at the energy of this photon, I'd be able to see this same structure. Okay? And so what something like that would look like is, essentially, instead of now looking as a function of square root s, so the energy of this photon just goes like square root s over 2, 1 minus the mass of this stuff over s. Okay? And so now as a function of E gamma in GV, so these light resonances are now going to appear as high photon energy particles, and the heavier the resonance, the lower the energies. So there's going to be some, so now we're going to see some, we're going to see the psi 2s here, the j psi here, and phi. This is, of course, not drawn to scale in any way, but you sort of get the picture of what I'm talking about. Okay, and this is in some normalization, some number of events in some sized bin. Okay. So this is what we have at a fixed energy machine. So for instance, if we took a machine such as Bell 2, which is going to be colliding e plus e minus at square root s of 10 GeV. Okay, so this is Bell 2. And they're expected to have 50 inverse Attobarn data. Then this is what the spectrum would look like if I was sort of ignoring the hadronics in the system. Okay, so imagine that all I had was a detector that could see photons. Okay, I could see and track the resonance structure of QCD by just looking at this monophoton energy. Now, of course, these machines are not perfect, and so at any given machine, you expect to have some energy resolution. So Bell 2 sort of optimized energy resolution is hoping to have maybe 1% energy resolution. Okay. And so what that does is, of course, sort of smears your spectrum, and so you end up kind of, so this is what that ends up looking like, ballpark at Bell 2. Okay, so in this case, these lighter resonances, you'll sort of see that something's there, but you won't be able to actually decipher them from each other. But these heavier resonances, you'll clearly be able to see. Of course, they're going to be slightly smeared because of the resolution of your machine. Okay, but this is what QCD would look like at Bell 2.
What is the resolution like on the plus or minus machine? I mean, if you scan the energy, how fine can you do?
Over here, I think you can get to very, I don't remember numbers to tell you, but I mean the fact that you're seeing, you really have this amazing, whatever, you're not really seeing any smearing here, right? You're really getting the proper width. Yeah. Okay, and just one more word over here. Of course, I'm talking about how I would see QCD at a machine such as Bell 2. Of course, you can ask yourself, what is the standard model background? And so this is coming primarily from EE to photon nu, or at least this is one irreducible contribution. And if you plot this in terms of, this is sitting way down here, so there's sort of, over here there's roughly 10 to the 6 orders of magnitude that you win with this signal of looking at QCD versus your background. Okay?
Sorry, just check my understanding on 1% energy. As the root test, so this is one particular root test.
This is at fixed square. So this is, what I mean by this is your sigma E over E.
So as the root test reduces, you get better resolution on the lower energy.
Well, this depends on your machine. So if I'm talking about Bell 2 towards the end, I'll tell you something a little bit about BESS, which is
the same machine at a lower root test. I mean, you get better resolution than on the lower energy QCD resolution.
Well, I think it's a question of what you have in your detector. So Bell 2 at the end of the this is the optimized at high photon energies. They hope to have somewhere between 1 to 2% energy resolution. Currently, what they think is that as they go to lower photon energies, they have their resolution gets worse. Okay.
Sure, this is 1% doesn't change.
What's that? No. The percentage does change.
As the root test reduces, then the energy of the photon of these low energy resonances will be lower, so you'll get a better.
If you were right, well,
in like a world in which the resolution was energy independent.
Yeah, but here it's.
But it's never really energy independent.
Right.
Yeah. Okay.
Yeah, and even this is the first naive thing you could do with as a theorist. This is not this is not what Bell 2 is exactly going to see. Of course, this number right now changes for them per bin, and they're still working on improving this resolution. Okay, so this is QCD, and now I just kind of want to show you guys how you can use the same idea to probe some dark sectors. Okay. So let me start with, I guess it'll be example number 1. Let's do something that is extremely similar. Let's look at some mirror QCD. Okay, so this is maybe some mirror model, maybe something that arises in neutral naturalness. But what I mean by this is what I just want to do is sort of copy this, just take the exact same structure, okay, and see what we could see if we had a mirror QCD. So in this case, let me just draw that diagram again. The way that I'm sort of going to be looking at this is, let's say I have E plus E minus. Okay, so here's my photon. And over here I have this vector. And what I'm just, for simplicity, let me assume that this is some dark photon. Okay, so it's a kinetically mixed dark photon. And then this is going to, go to all this stuff. So now instead of hadronic stuff, what I mean is now this is really sort of, let me call this dark stuff. Okay? So I have some kinetic mixing between my photon and hypercharge, which at the end of the day, so let me just write down my Lagrangian, is going to have some, let me call it epsilon gamma, and there's going to be regular photon, and let me call it dark photon. Okay? So there's going to be over here some epsilon gamma that comes in. Okay? And for simplicity, let me just assume that the dark gauge coupling is ballpark the same as regular, as our real world. Okay? So everything here is actually extremely simple, right? Because what you can see is that I'm just going to get now a scaling of the cross-section. So there are two differences. One is that I have now this additional coupling epsilon. And of course, now I also have, this guy can have a mass. So that sort of changes the propagator in this process. And of course, these types of, so kinetically mixed in photons have a lot of, are well studied in the literature, and there are all sorts of constraints on, as a function of the mass of this guy, what size of epsilon gamma I can have. Let me just sort of talk about two regimes. The first is when I'm beneath around 10 GeV. This is where there are constraints, lots of wiggly lines, but roughly constraints of order 10 to the minus 3 coming from Babar. Okay? And then once you go to around 10 GeV, there's some electroweak precision tests, which are giving something over here of order 10 to the minus 2. Okay?
Not going below the MEV.
What's that? Yeah, I'm not looking. Yeah, this is. I'm really going to be talking just sort of as two benchmark points. Let's say around a few hundred MeV-ish and a little bit above 10 GeV. Okay. So you can sort of think of the way that this. So because I'm taking the exact same resonance structure over here, I'm going to get something that looks very similar over here, with the exception of the fact that I can have some scaling that goes with this epsilon squared. Okay. So roughly my cross section. Or the number of events is going to have some epsilon squared coming in here. And then from the massive propagator, you can sort of expect to have something that looks like, so let's write it down. So I have some propagator here that's going to go like the mass of this system. Let me call this the invariant mass over here. Okay. So there's going to be something that cares about the mass of this guy. Okay. And so just for dimensions, sort of the only thing else that could be there is the mass up here. And so you see that if I'm looking at dark photon masses that are much larger than, say, the largest energies that I could be producing here, then what I'm going to get is some epsilon squared over mass of that dark photon to the fourth. Okay? Or else I'm just going to get this epsilon squared suppression. So if we said that in order to see this over here, I had around 6 orders of magnitude above the standard model background, that sort of limits the amount of playing that I can do with the dark photon because of these types of constraints. Okay, so if I was taking a light dark photon over here, I'm already basically losing these 6 orders of magnitude. So there's a little bit of room, but not much. And if I look at some masses that are, let's say, sitting at 10 or 20 GeV, I can now have a suppression of maybe 10 to the 4, 10 to the 5 compared to that rate, and so I can still be visible. Okay? Okay, so this was the first example, which was just basically taking a copy of dark QCD, kinetically mixing into the standard model.
Sorry, so the mirror case just has one resonance.
What's that?
It just has one resonance?
No, the mirror case has, I'm kinetically mixing, I'm taking this entire spectrum. So I'm taking the resonance spectrum of QCD to just be a copy, okay? And I have my dark mirror photon kinetically mixing into hypercharge of the standard model. So essentially, it's the same. If this was beforehand, the perturbative part over here was a photon or a Z. I'm just adding a kinetic mixing now between whatever it was into the dark photon, and then just like I could, right? Because I could have described all of this with, this is like vector meson dominance. So I'm just think of it as a photon mixing into stuff. Okay.
But I think what you're saying is that like that pie on the left would be exactly this. It would look exactly the same for the mirror QCD. Just scale down.
Right. So it's
identical location.
But how,
Yeah.
I mean,
But
you
then
have
how-
a selection, no? So
I was just going to ask, how do you then distinguish? How do you know that you're seeing dark QCD and not just QCD?
well, over here, so in the QCD case, this is really all going to, there's a lot of hadronic crap going in as well.
So
If all I was doing was looking just at the photon, if I had a mirror QCD, then it would look, so there's small differences. The locations over here would remain the same. The entire, because I'm taking a massive vector, so the entire shape over here, which is sort of slopping down, actually changes. So there is some difference. So these guys all sort of, there's a difference in the shape after, which my skills here are not exactly gonna show picking up.
Are you taking events where you
You would also see much fewer events. Well, if I was seeing as many events as standard model, that would be very, very suspicious. I mean,
Yeah, but
the parameter space gives you a suppression.
But are you vetoing on hadronic stuff? Is that?
Yeah, sorry, I should have said. All I'm doing, I'm doing a purely, so the idea is to do a purely monophoton. I want to look at a purely monophoton. Okay? Yeah, sorry, that's what I meant by I'm just tracing this. I can take this idea from QCD,
Yeah.
from the way that I could think of looking for QCD. This isn't what has been done, but you could have done it this way. And so based on that, what I just want to do is now, since I didn't need to see all that stuff, let me apply this to a situation in which I cannot see all this stuff. Okay?
how good are the detectors?
This is expected
No,
around
I'm
the.
thinking how likely are you gonna get a fake missing energy event from not seeing some stuff?
Right. So in addition to this, I mean, there's this standard model background, and of course there's also, I could have here 2 gammas, I could have here 3 gammas, I could have gamma LL. There are some ways, and the way that you'd miss this is if some stuff, went on the beamline or the beam pipe, or these guys were collimated, or something went into the detector crack. So in principle, if you have good knowledge of your detector cracks, you can try to eliminate that region. But this is the type of thing that, so there are some Bell 2 people who are interested in this, but I think that's.
But you would expect that it's smaller than the actual background.
Well, if you cannot mitigate those backgrounds, it would be bad. But I think that you should be able to, if you understand your detector properly, you should be able to mitigate those so that hopefully they'll be subdominant to this. So I'm sort of using this as sort of my limiting, if I want to be able to see or not see, just using this as a ballpark for how well I could do. Yeah?
Regarding the resonances that you would like to discover this way, does it actually assume that these resonances are decaying fast? Which
What-
would not necessarily be true.
No, so I'm looking, these are completely invisible, these resonances, I'm looking at completely invisible modes. So I'll demonstrate,
No,
I'm going to go.
I'm happy with this, that it's invisible, but let's say this gamma mixes with some pictorial blue ball, which then stays stable for macroscopic distances. You will not get enhancement.
So let me go through, let me demonstrate, let me go into some dark sectors that I want to talk about next, okay? And just show you I'm not claiming you could see anything in the world with this, but there are large classes of dark sectors which could be visible this way. So I want to give you some more examples of those.
But the enhancement appears exactly in the narrow width approximation, so an infinite lifetime gives you the same.
Exactly. That is what I'm trying to say. That it appears in narrow width approximation, while I'm not sure how valid is this assumption.
For the first example,
I'm taking mirror. Here I took mirror QCD. So I took this is my spectrum, and in
But the mirror QCD should decay very often.
No, look, the
mirror
row-
photons.
But you know the width. It's exactly the same.
Yeah.
It's exactly the same
I'm-
model.
the
Exactly.
row goes to 2 pions or 3 pions.
I'm going to do rows to 2 pions. Yeah.
2 pions.
But the mirror
So-
is exactly the same as the standard model QCD. So look at the widths. She basically drew them.
Okay.
And in the cases I'm going to talk about now, I'm going to be looking at the rows into 2 pies. So. Okay, so this was mirror QCD, how I'd look for it with monophoton. Now I want to talk about some other, I don't really know trying to think of a good title for these sectors, just sort of strongly coupled gauge sectors. So let me think about SUNCs or SP, NC, or SO and C. Okay, so these are the gauge groups that I want to think about, and the way that I've sort of been thinking about these for a while is related to some other work that we've done. So if I have some theories like this, and I have some NF flavors, or 2 NF flavors in this case, then in principle there are flavor symmetries over here that once the theory confines, you get some other flavor symmetry that's residual. So there's a variety of coset spaces in each of these cases. And at the end of the day, you end up with pions that are light and are stable because they can be, you can have these exact residual flavor symmetries, okay, under which these pions transform. And then you can also choose from these. So just to, so let's think of this one, which is very similar to QCD. So I have some SU NF cross SU NF original flavor symmetry. The theory confines. This breaks down to the diagonal SU NF, and I have pions that live in this coset space. Okay. And if I wrote down a mass term for the quarks, for the confining quarks, that preserves this residual symmetry, then at the end of the day, this is an exact symmetry. My pions transform non-trivially under it, and they're exactly stable. Okay, and you can do the same for these other gauge theories. And what's nice over here is that so you end up with a variety of different pions, and these pions are actually can be good dark matter candidates. So that's not something that's crucial for the story I want to tell you today, but this is just the way that we've sort of been thinking about these pions. And so these pions can be good dark matter candidates through 3-2 annihilations. And the other nice thing over here is that once I have a symmetry structure of this sort, it's actually easy to identify a U1 component of this residual flavor symmetry, which you can further gauge. And you can do this in a way where you still have another residual symmetry under which your pions are transforming. So really everything is perfectly stable, and the story is coherent. And so I'm going to be gauging some. Okay, so there's going to be these gauge groups, and there's going to be this additional. Yeah. Mm-hmm.
Does the Westermino-Witten term
Yes.
break the flavor symmetries or not?
No. Yeah. Exactly. So this is right. So I'm looking at all these cases where I can use this Westermino-Witten term for my 3-2 interactions to get me the right amount of dark matter. Okay. And and what we've shown is there are also there are these. You can choose smartly which U1 out of this residual symmetry in each case you can gauge, such that these pions are still there's still a preserved symmetry under which everything transforms. And so what I want to do in this case is just I want to look at let's look at the singlet rows. So these are rows that are singlets under these flavor symmetries. These are guys that can mix with. You can think of it as if they correspond basically to a similar generator as this U1 that we've gauged. And so I want to try to look for these singlet rows. Okay. And a useful method to think about this, about how I can think about their interactions, is to use is basically to think of these rows as if they kinetically mix. Okay, so these think of it as if I had my dark F mu nu, my dark photon kinetically mixes with these rows, and there's some coefficient over here. Let me call there some decay constant. So there's a whole tower of these guys over the mass of them squared, and there are also interactions between the dark current that's associated with this, and it interacts with, of course, just the photon, the dark photon, but also with some other coupling to these rows. Okay. So the point is, there's some way in which I can write down this interaction, and using sort of inspired by ADS QCD, we can write down some let's call it sort of guesstimates that relate these couplings and these masses and these decay constants in a way that then can give us some modeling that I can show you some plots and some results. Okay. So what this effectively does, so I have this row. Okay. So I have some row, a tower of rows over here that's kinetically mixing into this dark photon, and this dark photon is kinetically mixing into my regular photon. Okay? Okay. Where is the... Okay, so the first thing that I want to say about this is that, and let me just what you get from this modeling, this is the only part that sort of, is that I can write down this whole tower of these singlet rows as just an integer times sort of the first one. Okay, so I specify the first one, and now I know the tower. So the first thing that I sort of want to note over here is that, usually we're so used to thinking of these constraints for dark photons, right? I have the kinetic mixing versus the mass. But if this hidden photon has this entire row spectrum that it also talks to, then instead of just plotting these kinetically mixed, epsilon gamma versus the mass of that dark gamma, I can actually take the same types of searches and place constraints for a fixed dark photon mass actually on all of these dark rows. Okay? So what I mean is say, okay, because if I take, a Babar process, if I take let's say Babar, they're looking for dark, it's just basically looking at monophotons. So instead of saying that this thing that I haven't seen on the other side is this kinetically mixed hidden photon, I can further translate it into these dark rows. Okay? And that gives you sort of a new plane. So let me still look at epsilon gamma. Okay, so I can translate, this kinetic mixing onto that kinetic mixing. And so you get some constraints. And so if this hidden photon, you can think of this in both of the regimes of a very heavy or a very light hidden photon. Yeah, so if I have, let me sort of take this in the region where this hidden photon is above 10 GeV. Okay, so we know from here that the constraint on epsilon gamma, just from the direct search for the hidden photon, is around 10 to the minus 2. Okay, so I have this 10 to the minus 2 over here. But then I can take the same search for Babar and interpret it now as what type of bounds do I have on the mass of these rows. Okay, and this is, let's say, up to 10. Just looking over here, and those are actually pretty nicely sitting lower. Okay, and they're also, basically think of any type of constraint that you're used to thinking of in this parameter space. So projections for Bell 2, if I was looking for just the monophoton, not doing spectroscopy, just looking at what I could probe, then also those constraints go very nicely deep into this parameter space. Okay? This is a new type of parameter space that you can be thinking about, not just the hidden photon, but rather what type of constraints could I put on hidden rows. And if I had a lighter hidden photon, let's say 200-ish MeV, well, in this case, the constraint on epsilon gamma is already very strong. So that's, again, 10 to the minus 3. The direct constraints on these rows from Babar are sort of sitting up here. Okay? And the Bell 2 reach is very, very borderline. Okay? So this is the first type of thing you can do if you think really of some strongly coupled, if you have a strongly coupled hidden sector, these dark row resonances themselves can actually have constraints from the same types of experiments that you usually think of for the hidden photon case.
So what happens exactly for when the masses are equal? You cannot distinguish.
Yeah, then basically it's you can sort of think of it. You're picking off from the Babar curve. Let's say if I'm in the low mass region, from the Babar curve, I'm picking off that exact value. So they're exactly going to be touching. Okay. Okay, so before we go to actual spectroscopy, so this is the first point I wanted to make about these rows, that there's a new parameter space which you can be constraining over here. And the second thing is that thinking about the spectroscopy, which we're talking about, is that in principle, if I have some spectrum of these rows, if I want to be able to separate them, if I want to be able to see them, then at least I need for the difference in these peaks to be larger than my energy resolution, right? So that I'm not just binning everything together. And what that gives you, so I want basically the difference between two neighboring resonances in terms of that energy of the photon, I want that to be roughly larger than my energy resolution. And what this gives you is that, at least in this if I take this relationship in the spectrum, what this tells you is that the mass of your lightest row should be roughly larger than square root s times this, your energy resolution. Okay? And so if we talk about something like Bell 2, where we're colliding things at 10 GeV, and this energy resolution is, let's say, 1%, then what you learn is that you'll be able to see this if your lightest row is roughly a GeV or above. Okay? If you go to lower masses, you're not really going to be able to do a good job. It sort of at least guides you in terms of what conceptually can or can't be done. What's that? Well, I'm going to show you. So they're not extremely narrow. I'm going to show you what a spectrum looks like now. Okay? Okay, so let me go into the first example. Yeah. Mm-hmm.
Well, I think that kind of answers your question, right? Based on the less energy, the masses can be lighter because they're more spread.
Yeah. Right.
Yeah. So that.
It's in the same direction. Maybe I'll ask.
Yeah. And I think you'll see in the last part I'll show you will be a case in which Bess can do better than Bell. Okay, so let me, for instance, take an SU2 gauge theory with 4 Weil fermions. And I think I'm taking over here. So let me take M, the lowest, so the pion is going to be a GeV. Let me take the lightest row to be 4 GeV. And let me take a heavy hidden photon, so somewhere, let's say, just above 10 GeV, 12, 15. And that means that the constraint on my epsilon is I can take a pretty large epsilon. Let me just make sure yeah. Okay, so I can take this epsilon gamma to be of order 10 to the minus 2. So here's what the spectrum looks like. Say something roughly like this. So here's my row 1, my row 2, my row 3, etc. Okay. And this is going to be number in events, and I think these are 100 milli-eV bins. So this one is appearing here, photons energy. So this is just ballpark. This is at what photon energies these appear. So this one is, let's say, around 4.5. This one is at around 3.5, 2 point something, etc. Okay? And when I smear this and bin it with this 1% energy resolution, it really just looks extremely the same. Okay?
So
yeah.
In this case, you also get baryons, which are...
Well, for the SU2 case, I don't have baryons. This is like an SP2. There are no baryons here.
Okay.
Yeah. Yeah.
What is the relative heights there?
What's that?
The relative heights. Are you doing it linear or local?
This is over here. This is on a log scale. Sorry. So let me just add some. So let's say this is of order, 10 to the 5, and down here is around 10 to the 4. And standard model background over here. Sitting somewhere very low. This is probably not exactly scale, but yeah. So what I'm doing here, sorry, I should have said what I'm assuming over here, because I do have these light pions, is I'm always taking, and you notice this in terms of the parametrics, I'm assuming that my rows are decaying to dark pions. Okay, and then you use this ADS QCD to model your widths. Okay. Okay, so this is just to show you, this is what it looks like at Bell 2 with 50 inverse attobarns, and this is very nice.
Epsilon gamma 10 to minus 2.
Mm-hmm.
Are you safe with mixing with our QCD states?
Yes, well this is, if I'm taking over here, this is an example with a heavy hidden photon. So the size of epsilon gamma can be up to 10 to the minus 2. Okay.
No, but I'm saying up for the A prime of the gamma D, I'm saying this rho that's became to pi r,
Mhm.
does it have some level of epsilon gamma squared mixing with any of our Qcd metrics?
Well, it can always mix. So the way that it talks to anything in the standard model is through mixing through. It goes via the photon, and these constraints give you everything is perfectly safe. You don't have anything.
Mixes with rho, but it's going to be 10.
No, but he's talking about the. Yeah.
I guess so. Yeah, put another row on the left side.
Yeah. So once I get to here, I can always do further stuff. But that's entirely. If you've taken something that's safe over here, you're safe.
No, but I mean, I accept that the left constraints above, say, 10 dB are fine, or the bar direct searches, but if you do these searches allow them mixing with Qcd mesons,
I guess
as people calculated?
you worry about decays, new decays of the.
Yeah.
Yes.
So we worked out that the branching ratios are super tiny. So once your row can decay strongly, it will decay strongly.
I think you
Yeah,
can
but
set
even
model.
our mesons can decay some epsilon squared.
It would be weaker than
Yeah,
the constraints coming from just hidden photons.
Yeah. That's what I'm saying. That stuff it's going to be weaker than this. So once you're safe here, you should be safe with that. Okay, and one last example. So let me take an SP4. Still going to take 4 wild fermions. And let me take my pion, my dark pion, to be around 500 MeV. I'm going to take the lightest row to be just above twice that of the mass of the pion. And let me take here the hidden photon mass to be 3 GeV. Okay? So I just write that plot, but because I'm talking about 3 GeV, I'm constrained by Babar. Epsilon should be 10 to the minus 3-ish, a little less. Okay? And so if you look at this at Bell, what happens is, so I have this dark photon at 3 GeV, and you're going to see that one. But what ends up looking like is sort of, you see the peak of the dark photon, and there's like a lot of other resonances appearing over here. So this over here corresponds to the actual dark photon. So this one you're going to visibly see. But once you include, so let me write, this is at Bell. So once you include the smearing with the energy resolution, and you bin, you really just see that dark photon. Okay, so you're not going to be able to see, so dark photon, good, and resonances, bad. Okay? What's that? No, over here you see that it's heavy. There are also some, yeah. What do you mean by in the? Well, it has to do. I mean, what's happening over here? There's a, in the way at least that we modeled it over here. There's of course a relationship between the masses. So I have a relationship between the K constant, mass of the row, the effective kinetic mixing, and that's also dictating my my decay widths. Okay, and so you can play around with some. What's happening over here is just that these resonances are so extremely close to each other that just in terms of your energy resolution, you're not able to see them. Okay.
What is your dark photon width?
What's that?
What is your dark photon width?
The dark photon width.
It's saying narrow. Why is it what you?
Well, it's wide,
Yeah.
Why is it wide? Or what is your?
because there's so many plans for these.
Yeah. I mean, I can give you the. I can show you the expression later, but
Order
just,
one gauge coupling.
yeah, it's an order. Yeah, it's an order 1 gauge coupling. I have NC, I have NF. It's just there's a lot of stuff for it to go to. Okay. Okay, so at Bell 2, you'd be able to see this dark photon, and you'd be very happy. You wouldn't be able to see any dark resonances, though. And so what you can think of doing is looking at a lower energy machine at a smaller square root S. So this is, for instance, not exactly what BESS is. So BESS, this is really would be sort of beyond BESS 3. I'll show you in a moment why. But this is something that operates at sort of square root S that's around 3 to 4 GeV. Okay? So it's a lower square root S, and what that essentially gives you is a larger spread in E gamma of the location of your resonances. Okay, so you end up with something that... Yeah, and this...
To go to a local X to see the resonance.
Yes, that's exactly, yeah, and that's what I was, yeah, that I was going to show you this plot at the end. Okay, so I have here E gamma, and again, some number of events, and essentially, so here you're able to see, so what happens over here is so the way I drew it right now, you're seeing all of these bumps. Okay, but if I look at, once I smear it and bin it, what happens is that, and I have my standard model background, let's say, somewhere over here. Okay, so you end up with, so if I take this BESS 3, the reason it's not exactly BESS 3 is because BESS 3 is expected at the end of the day to have around 10 inverse femtobarn. And what I need in order to see it over here is probably an order of magnitude more. Okay, so this is more like a higher luminosity, similar low energy machine. And what you end up over here is, let's say if I look at how many events per bins of 40 MeV, then over here we have maybe 100-ish events. Over here we have maybe 10-ish events. And over here we're already sort of in the area of just single events. So what that means is that, when you look at this binning and smearing, over here you end up with stuff that has very large error bars. So you're not going to be able to actually see these low guys. But as you get higher, you sort of, not doing the best job of this, but in this case, what you'd be able to see is sort of the higher resonances. Okay, and that's exactly thanks to this lower energy gives me a bigger spread between my resonances in the E gamma distribution. Okay.
Yeah, that they already had the kind of same width, or so the
What's that?
resonances at some point get very wide.
No, I mean there's some obviously there's some dependence on the mass through through standard beta, but
But how is this in QCD? I don't know.
so here let me tell you how we modeled it. And so for the width of, so this is rho into dark photons, we use something that looks roughly like, there's a beta cubed, 96 pi, there's this coupling over here, and its mass. Okay, I mean, so this is a particular model so that I can, or it's a class of theories that I model via ADS QCD. But of course,
one row decay to another.
What's that?
That's not letting one row decay.
No, this is looking at the decays into two dark pions. Yeah.
Well, I don't know. Okay. It's probably not very QCD like this theory. So I guess that's the point.
Well, yes, it's not, I mean, you see the structure over here. This is, and all I'm doing is really talking about this singlet rows. There are lots of other things that you can search for in other ways. Okay, that's kind of all I wanted to tell you guys. So we can do dark spectroscopy at left-hand colliders. Thank you.
Okay, so we have time for more questions.
Yeah.
Can you do the same exercise with the fixed orbit experiments?
We think the answer is yes. We just started looking into that.
So all of this is sort of proposals for future experiments. These monophoton searches have never been done before.
Well, people have done. I mean, the way that this Babar constraint on epsilon gamma. These are monophoton searches. I think the idea I was talking about here is like so extremely simple that we were very surprised that it hasn't been proposed. It's just let me not just place some bound based on what I don't see in a monophoton event, but let me think of the energy of this photon as a tracer for a system it's recoiling against. And so this is something that crucial to be able to do this is that these these machines have to have some monophoton trigger, which is something that's fairly difficult, and so Bell 2 people are definitely hoping to be able to do that.
Okay, more questions? I'll ask you a question on a different topic if no one else has questions on this topic. Someone else a couple days earlier talked about doing some hadronic collider spectroscopy games for missing energy that I absolutely don't understand. And since you talk about spectroscopy and dark stuff, I wonder if you looked at it and can explain anything.
Well, I need to tell me more details about which particular proposal.
Yeah, I'm trying to remember. They talked about building something out of various shapes in the Hadron Collider where they have already convoluted the result with the PDFs and everything, and they claim they can actually measure the mass of a dark mediator in this way.
Okay, so I haven't done those. I haven't written that paper, so yeah. All I can say about it over here. So I think notice everything I'm talking about here is how to probe a light. So these are light dark sectors. Okay. Usually, there are ways to look for these light dark sectors also being produced at the LHC, for instance. I think that I'm not 100% sure. My guess is that the type of analysis you're talking about is a less light dark sector, but I think it's a heavier dark sector, but I'm not positive.
I recall it was sort of, it's the same level of light for the LHC that this is for Bell.
Okay, right. Just saying these are very different mass scales. Very different mass scales. I think I hope that what I've managed to get through here is that this is other than the fact that obviously it's always very difficult to do to have this monophoton trigger, but in terms of this is everything I told you here was like super simple, super in principle clean. Just to look at the energy of the photon. I'm not playing any other games. All I can say is about the stuff that we wrote, less about somebody else's work. Yeah.
Just a question about the models. In those examples that you presented, is it accident or not that you use SPN groups? And in general, what are the theories that? How are you building these theories that you would like to?
Oh, so no, it just happens to be. This is an SU2, which is also an SP2. No, but as I said at the beginning, you can 100% do this. This can happen for an SO, for the SP, for the SU. These are models that I can tell you exactly which U1 in the end of the day you gauge, such that you have a totally sensible theory in which you actually also have automatically dark matter through these pions in 3 to 2. So these are, this is not a single. It's not like a single model. These are really generic classes of strongly coupled gauge theories that you can be playing with this way.
But should you actually insist that every of the models that you're looking on actually does have pions as pseudo-Wilson models?
It doesn't have to be the case. These happens to be the ones that we've played with a lot, and so I know, I have machinery in which I can easily show you what they look like. These are by no means meant to be the only models in which you can do this. This is my way of demonstrating it as an in principle method for doing spectroscopy.
So what would change if you take a model where you literally don't have pseudo-Wilson bosons and rho is essentially has roughly the same mass as all other particles in the theory, so you don't have a mass gap between the pion and the rho?
Well, everything here, these are really strongly coupled theories, so all of these resonances are ballpark sitting in the same place. All I cared about over here was that I was producing a particle, I was producing some dark resonance that decayed invisibly. So you can also look, and that's also work that's work that's been done by other people, where you look at, if in principle you have some vector that's going into, decaying into leptons at the end of the day, there are other games you can play this way. What we wanted to do is really just look at this monophoton and see what we could do.
But I guess the first thing that happens is your resonances get more narrow and easier to see.
But so that,
If you take away some large free energy decay modes,
right. So take any, depends, I think, take any dark sector that you want, any light dark sector, however you want to model it. This is a method in which you could probe it, assuming that it has some type of coupling to the standard model. And you can figure out which of the resonances, based on quantum numbers, et cetera, which are in principle seeable or not seeable.
all right. So let's thank Yonit again.